Hello everyone. I'm Favour James from Buffalo University, Nigeria, and I'm excited to share with you my work on using large language models to extract molecular interaction from scientific text. This work is in collaboration with TextToKnowledgeGraph and Augustin Luna. I acted as a software engineer in this project, and I will be discussing why we are using LLMs to extract Bell statements, how the code works, and future directions for this project. Knowledge graphs are powerful tools for structuring biological information due to their ability to represent data across different data sets. However, constructing these knowledge graphs for scientific literature can be very challenging due to the expertise that is required for manual curation. And different works have used traditional text mining techniques, but they have limitations that affect their ability to actually capture complex biological interactions. So these traditional NLP methods, they struggle with understanding context because some of them don't have the expert level background knowledge that you could use to infer relationships that are not directly described in a text. Bell stands for Biological Expression Language. It was chosen because of its ability to represent biological relationships in a compact and in a detailed way beyond mere protein X binds protein Y statements. So here we can see a statement about phosphorylation at a specific residue being mediated by multiple kinases. So essentially, AKT1 is acting as a kinase, a form of enzyme that transfers a phosphate group onto another protein. So in a kind of way, it slaps this phosphate group onto HSF1, which is the protein at the serine 326 spot. So this small chemical tag is also known as phosphorylation, which can change the shape of HSF1 and in turn increase the activity of HSF1 or trigger further interactions. That is what is represented in the statement that is shown on my screen. And this is one of the multiple statements that was gotten from the sentence phosphorylation at S326 is mediated by AKT1, mTOR, P38, MEC1, and the last entity. This tool has two main input modes and one output mode, which a user can use. So you can either input a PMC ID or your local file in the PDF or text format. So PMC ID stands for PubMed Central ID, which we use to fetch articles for Pubdata. If you have a PMC ID, Pubdata is a Complex Central is a database that you can get free scientific text of scientific articles. So if you provide a PubMed Central ID, the tool automatically fetches the article text from Pubdata. Or if you upload your own file, either in the PDF or in the text format, this file is passed locally. Then the text is processed using our pipeline, and then you get an output. The output that we get from this tool is in the CX2 format. CS2 format is a standardized JSON-based structure for Cytoscape, which captures nodes, edges, and visual styles that you can easily load or visualize the network in Cytoscape or Index. So essentially, once you get this output, Cytoscape can render it as a form of knowledge graph with all the Bell interactions in it. There are two options for using this tool, either as a Python package or using it in the Cytoscape web, which is going to be publicly released. So whatever method you choose to use, you would get the same output, which is a CS2 network that can be visualized as a knowledge graph. So for the processing pipeline, once the user inputs either a PMC ID or your local file, and we extract the text from any of these two inputs. The next thing to do is to convert it to a list of paragraphs. These paragraphs are then sent to Gilda. Gilda is an API that is used to annotate entities. So Gilda grounds this entity, the entities in each paragraph grounds it to standard identifiers such as HGNC for AKT1. This is to actually ensure we have consistent and unambiguous references for each biological term. So each paragraph with the annotated entities is now sent to our LLM module. In this case, we made use of GPT-4o and Claude 3.7. So the LLM module processes the paragraph with the annotated entities and extracts Bell interactions from each of the paragraph, extracts valid molecular interactions. Then the LLM now outputs this Bell statement in a structured JSON format. It will essentially be like a list of relationships. Finally, these statements are then converted to the CS2 format, which is the method with which you can use to visualize it in Cytoscape. And the result is a fully formed knowledge graph that actually contains all the extracted interactions from the science text that was uploaded in the input. So a major component of these two is the prompts. So the prompt is what guides the LLM into extracting and structuring interactions. The prompt is structured to provide the LLM with the insertion knowledge required to create Bell statements. So the prompt is 80% of the Bell manual. The Bell manual contains of the Bell biological functions, the Bell relationships, and some usage examples. We also tell the LLM exactly what to do, and we let you know that it's acting as a bioinformatics expert. We also give you some strict guidelines because the prompt is divided into sections. In the strict guidelines section, we tell it to only use the annotations that are provided to avoid made up entities or made up namespaces. We also tell you to ignore sentences that don't have at least two annotated entities. But you cannot, because you can't have an interaction without two entities. And then we also tell it the output format which we expect it to give us the Bell statement in, and we give it few short examples. Few short examples are just examples that show how a statement is scientifically structured in Bell, a correct scientifically structured example. So we give it some examples in order to help it know how to extract correct interactions. So as mentioned earlier, I spoke about grounding that is done by Gilda. So before we ask the LM to extract interactions, we actually need to make sure that every entity mentioned, like AKT1, is actually mapped to a standard identifier, and that is what this is where Gilda comes in. Is an API that we use to ensure that the entities in each paragraph are actually grounded to the standard identifier. So, for instance, it will see it gets takes AKT1 and it returns HGNC 391. This is to actually ensure that we have an unambiguous reference to a particular human gene or protein, and this also ensures that the model will produce Bell statements with correct identifiers. Why is this useful? Imagine we have multiple papers referencing the same protein but calling it different names. By grounding all of them to the same identifier, we can actually merge these interactions later without accidentally treating them as different entities. This means that you can build bigger, more consistent knowledge graphs because you have grounded everything to a particular entity. So how do you make use of this tool? As I said earlier, you can use it as a Python package. For a Python package, you can either use it in your command line or your code. This tool can accept multiple PMCIDs, PDF parts, or TST parts, and you also have to input an open key, enable the model run co- correctly. So here is an example of the final CS2 network for one of the papers we tested in Cytoscape. Here we can see each node corresponds to a Bell entity, and each edge which is connecting the nodes is like a relationship from the text. So you can see clusters of proteins and processes. This generation can actually help domain scientists to quickly spot interactions or pathways. Here is a more precise single line representation of how the model outputs our example in the slide 3. So it shows the kinase activity of AKT1 directly increases a phosphorylated form of HSF1 at SCL326. So because this interaction was implied in three different sentences or paragraphs, that is why we can see there are three edges to show that okay, this interaction was actually implied in three different paragraphs. So something that I gained especially from this project is that we found that structuring the prompts carefully with strict guidelines, examples, and the bare manual, which was a major part of the prompts, was very essential for high quality results. Without thorough instructions like this, the model tended to produce inaccurate statements, incomplete statements, and scientifically incorrect statements. But structuring the prompt like this, we tended to get higher quality results. So currently, evaluation of the Bell statement provided by the LLM is being undergone by Bell experts. So Bell experts are currently judging the statements to ensure that they are structured correctly according to the Bell format and they are scientifically correct. So this tool is going to be integrated into Cytoscape Web, and once Cytoscape Web is publicly available to Cytoscape users, Cytoscape Web users can just make use of this tool as an app in Cytoscape Web. This is currently how it looks on Cytoscape Web. It has been imported as an app into Cytoscape Web, which once Cytoscape Web is publicly available to users, they can use it without having to install the package directly on their local system. Thank you very much for your time and attention. I would like to acknowledge Cytoscape Consulting for their funding and the rest of the people. Here's my LinkedIn if you'd like to connect, and I've attached the project GitHub page and Python package if you'd like to try it out. Thank you once again.